Hello, good evening, bon vespre. We are pleased and honored to have Michael Hansmeyer with us today. Before I start going a bit through his career and the work he's done, I would like to say that he has a very interesting background because he is now an architect, a designer, but he started as a programmer, and he started working in the field of stock markets, consultancy, etc. And at some point, he had a sort of a revelation. He was telling me that he was watching an opera play, which was an opera play by La Fura dels Baus. La Fura dels Baus was the set designers and choreographers, maybe? I don't know. Well, and he had this revelation. He said, I need to do that. I need to do this. I need to to go away from the stock markets and Wall Street and get into design. So this is when he decided to go to Colombia to study architecture. He made a master's program in Colombia. So it's very interesting that he comes from a very different world, and he decided to move to the world of architecture and design. He's an architect. He's also a programmer, as I said. And he works in the juncture of architecture, programming, machine learning, and visual arts by designing and using algorithms to generate and fabricate architectural form. He calls his practice, as I read, computational architecture, and he studies the relationship between the designer and the computer, so the man and the machine, being the machine an active partner in the creative process. So in this process, the machine is no longer a tool that the designer uses to implement or control the ideas he has previously conceived, but he's more of a colleague, of a partner, or even the creator itself, which is capable to expand the artist's imagination and push the bounds of what is possible, only being supervised by the human. In most of his projects, not in all of them, but in many of them, he produces objects that have not a practical function, and their purpose is more to evoke emotions, to be beautiful, so to provoke an aesthetic experience. And also, these projects aim to expand and push the imagination and envision maybe what the future of architecture could be. So his spaces are not designed in the usual sense, because, as I said, it's a process where the human or the artist, the human and the machine, the other artist, are working together in this sort of partnership where sometimes the machine is more autonomous and sometimes it's less, I guess. His recent work includes the architectural, the digital grotesque series, this tower, the tallest 3D printed tower in the world, which is built already or being built? Being built. It's still being built in Switzerland. And he has, many of his projects have been presented or exposed in some of the most important museums in the world. Part of his work is in the permanent collections of the Centre Georges Pompidou. And as an academic career, he has taught as a visiting professor at the Academy of Fine Arts in Vienna and the Southeast University in Nanjing, and the ETH in Zurich. As an architect, he has also previously worked with Herzog de Meuron, Swiss architects, and the rest of it, Michael will tell you. So thank you very much, Michael, for being here.
Thank you for this very kind introduction, and thank you for the invitation to be here and to be part of your lecture series. I'm very excited to be here. I named this talk Tools of Imagination, and I think if there's a basic idea behind it, it's the idea that we're transitioning from using the computer as a tool for efficiency and control, and we're moving over to, and you're seeing this with AI, I think very strongly now, as a tool for exploration. And it's a tool, I think, for expanding one's imagination. It's a muse and a partner. I'll start by asking, what can we calculate today? And this video is a bit older, but bear with me.
I don't think there's any question about it.
Will computers ever be able to work out what 9999999999999999999 multiplied by 9999999? Yo, I ain't finished. You don't know what I was going to say. 998999999.8899889 99999999999.
The answer is yes.
The most powerful computer in the world today does 36 trillion operations a second.
So would it be able to multiply 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10? You don't know what I was going to say. Multiply, you don't even know. 10, 10, 10, 10, 10, 11, 11,
It doesn't make any
12,
difference.
30,
Whatever
40,
numbers you name, the
80,
computer
90,
will be able
20,
to handle it.
100, 100, 100, 100, 100, 100, 100, 100, 100,
Yes.
million.
Yes.
Thousand,
Yes.
million.
Yes. Whatever
Billion.
numbers you want,
And
it will be able to multiply.
0.99998
Yeah.
without blowing up.
Yes.
Going to move it on a little bit. Where did men come from?
Men evolved out of
I don't
lower
think there's any-
species.
So I could watch this all day. But I think the other question is, what can we fabricate today? And you're looking at here a very large printer, which we've been using. You get an idea of the scale of it by looking at the door that's right there. And it can print massive pieces out of sand, 4 by 2 by 1 meters, up to 13 tons. And it does so at the resolution of about 1/8 of a millimeter. There's a massive print space, and one way to think about it is, for each sand coin, which one actually gets glued and which one gets sucked out in the end. It's 33 trillion different decisions to be taken that somehow one has to specify. The interesting thing is the complexity. There's complexity at no cost. You pay only by the dimensions of what it is you're printing, whether this is a plain and simple box like the stage or the most sophisticated form you can think of, the cost is the same. And there's also customization at no cost. So whether this printer prints the same thing 100 times or a unique form each time, the cost is also the same. Finally, there's very few geometric constraints. It can print basically anything. And I think I'm perhaps exaggerating a bit for the sake of the argument, but in short, there are very few constraints, neither on the computational side nor on the fabrication side for us. And I think we're in a curious situation, perhaps, where we can fabricate more than we can design, perhaps. How can we exploit this freedom? Is it through new design tools? Is it by is it computation? Is it AI? Do we need a new design language? I don't know, but I think we should try to create what is previously what has not been seen, and I would argue we have these tools at our disposal already, and if not in the field of architecture, we're going to have them very, very, very soon. I don't know how they can be used or towards what end. I don't know exactly what they imply for the role of the architect or the designer. I don't have answers to these questions. But what I am going to do is show you 2 or 3 projects which are very personal interpretations of explorations and trying to contemplate these tools. So I started out at Columbia, where I was studying, where I was hoping to somehow escape the architectural references that we've been taught in all the history classes. It's a very naive approach. It's impossible to unlearn what you've learned. But I thought perhaps I can find an answer in the computer. Traditionally, architecture is arguably an addition of different processes, of different elements and components which are put together somehow. Or maybe it's a subtraction of material as you are, I don't know, carving wood into a beam and so on. I looked at division, and it's a very simple process. It starts with a form, which is what you see on the left, and it just divides this form, in this case a square, into smaller and smaller and smaller forms. And I thought, if we just change where we put the midpoint, where this midpoint of the division takes place, and repeat this process a few times, then I thought, okay, some sort of interesting things are already taking place. And we can run it with different parameters, and different things occur. Super simple. I mean, the script has 10 lines of code, if at all. And I thought, okay, as an architect, let's see if it also works in 3 dimensions. The analog of a square is a cube, and if we take this, cube and divide the sides just like before, the cube will turn perhaps into this. Or if we apply a different weighting of where the midpoint is, it will turn into this, or this, or this. The 6 sides of the cube have been divided and divided and divided over again until you get to, I don't know, 10 million or 5 million different little facets which make up this form. But at heart, they're all cubes. To me, it was interesting because it's a very minimal process. There's a simple input, a cube, and a very simple operation, dividing, which is in a way much like folding. And yet you can generate something which doesn't look so minimal. And then in playing with this, you can apply different parameters at the top, at the bottom of the form. In this case, three cubes were stacked on top of each other to begin to somehow form the shape, or to exert some sort of a control over it. Are these processes parametric? Are they procedural? Or does that even mean anything today anymore? I don't know if it's a black and white distinction between the two, but I think it's, to me, there's a slightly different notion in terms of, with a parametric approach, I always think one is adjusting perhaps parameters of a system that we've kind of already defined. Whereas with the procedural approach, I think we may have the possibility to create something that is new and that is unanticipated. And I think that's part of the interest to me. So this is the same process a little bit later. Computers have gotten stronger. There are more little facets to be had. And in each case, it's the process is deterministic, but things are not entirely foreseeable. I don't know how this is going to turn out right here, or that, or that. It's simply it's a different way of working, because it's a bit of a trial and error. It's a little bit of trying to figure out what parameter creates what kind of an effect. It's a back and forth. There's an element of surprise. How can one bring this sort of a process to architecture? I mean, this was what I went back to school for. And I thought, let me try with columns. Columns were appealing to me for the simple reason that I think for many centuries or in different cultures, columns have always been an expression of some sort of a value system, some sort of a belief system. And, but there's another thing which I found very appealing. As Mario Carpo, the theorist, pointed out to me, in Vitruvius, there are no pictures of columns. They are simply written directions, written instructions for craftsmen how to create these columns. Divide the column along 8 different units, and then extend a little bit on the bottom, make something floral at the top, and so on. And it was the artisans who then improvised or interpreted this. And I thought this is interesting because it's a little bit like writing a script, and the computer playing with a degree of randomness can begin to interpret something. Here is a column that was created with the exact same process I showed at the beginning. You can run the process again and again and to create different permutations of something. And you can run it for longer to get more articulation, to get a higher level of detail. So to me, what's fascinating is it's a single process that creates the overall form and these little details and surface articulations. So I think in working with these new tools, and whether this is computational writing code or whether it's AI, to me it's really about a search for a search mechanism, because there are so many different permutations you can create. There are so many different variations you can create. The space of what is possible is so big that you have to somehow find some sort of a process to navigate the space. These are, this was for a competition entry for the Venice Biennale pavilion. And I was at ETH, where I had the fortune of having a good workshop, and we thought, how can we bring something like this into the world? 3D printers, the 3D printer I showed you just a little while ago wasn't quite there yet. And the only way that I knew how to do it was to divide the form you just saw into very many different layers. 2,000, 2,700, that's what you're looking at now, actually. It's like an X-ray through the form along the vertical. And then we laser cut it, layer for layer for layer for layer. It took forever. But it kind of worked, in the sense that the column that came out, which was some 3 meters tall, looked remarkably like the one in the computer. And what was the most interesting part of the project to me wasn't the column, but what was left over. We had always cut the column out of a big sheet of paper, and we stacked the remaining, the negative, so to say, on top of each other. And this is actually the negative space, which we had never seen or visualized before. You have to imagine this is me with a very wide-angle camera in the negative space of the column, trying to photograph it and see what kind of a form that produced. I like this picture a lot because you can see very much there's traces of the process that created it. So you can see the burn marks of the laser cutter, because we just got so tired of waiting for it that we turned up the heat hoping it would go faster. Certain things start to catch fire and burn off. You can see, I don't know, you can see parts that broke along the way. But nonetheless, I was delighted to be inside this cave, which I hadn't quite anticipated. A follow-on project here in Guangzhou. These are made instead, same technique, but out of ABS plastic. And this allowed many layers to be cut at once, so it was a little bit faster. But there's a big disconnect between the physical and the virtual. I mean, the physical, these forms compute in 30 seconds, and then to build it took some 200 hours. And I promised myself to never, ever do it again. And then I got a call from a company that made this machine. It's an incredibly fast laser cutter. It does something like 500 sheets an hour, and it strips the remaining pieces of paper off. And this allows you to essentially, you put the data in the machine, you go out and you have a coffee, and then you have 30 centimeters more of a column. Very cool to work with. These are a few columns that were made with this technique. The sheet is so small, though, that you get a warping effect, which wasn't quite the intention. I'll show you one more. And again, we're talking about the same process as used before. There was a lot of critique in the sense that people said, okay, they're nice, but there's no context. Everything, you're just creating these fantasy objects which have no use to the world around us. And I got a call from a architecture office that wanted to redo a building in Soho in New York, which is a historical district where you have a lot of cast iron buildings. Most of them are beautifully restored right now. This was one of the remaining ones that wasn't. And all that was left over of the column capitals was this. It had completely decayed and rusted away. We knew that at some point the columns might have looked like this, but we weren't sure it was the same building. And they wanted to know, can we use these algorithms? Can we use, and if we feed in as an input form, not a cube or a square, but if we scan this and put it into the computer, can we try to recreate some sort of an column shape that matches the original a little bit and uses these proportions? And these are a few of the variants that the computer and I came up with. They're quite conservative, I think, because we were very mindful of the fact that it's a historical district in Soho, and they don't like experiments. They want it to look as if it's something that's been there 100 years. Here is the printed and then cast part of it, and I'm a little bit embarrassed, but when I walk by it in New York, I don't even understand that that I did it, because it looks so similar to what else is out there. In a way, it's a missed opportunity, I think. We could have gotten a bit wilder, a bit more expressive, but I'm not sure that was possible given the historical limitations. We tried casting a form. And came up with columns with a big degree of resolution. And here you go. This is the actual cast that came out. Not successful. The process simply wasn't able to bring out the form as it was in the computer. So after that, I went back and started over, and went back to paper. And I thought, how can one use paper or cardboard in a manner that is slightly less time intensive? This is also for the Guangzhou Biennale, very limited budget and a very limited time, but the similar algorithm used as before, except that I said, let us not divide the entire form consistently. Let us create certain parts that are more divided and other parts that are not. And then you get this variation that begins to take place, almost a lace-like variation. And this is also essentially laser cut paper, different layers glued on top of each other. And I think from design to opening, we had less than a week, or at most 10 days. So it was, I was amazed at how quickly it came together. This idea of selectively subdividing something, of selectively articulating a form, more here and less here, and the patterns that then arise, reminded me a bit of muqarnas, which you have some very nice ones of in Spain, actually. These Islamic ornaments that you find often in transitioning a square foot plan to a more rounded dome. Here is one from the Topkapi scroll. For those of you who are interested in muqarnas, there's an excellent database by a Japanese guy, Shiro Takahashi, who has cataloged every single muqarna in the world, along with photos, the system behind it, the system that was used to generate these articulations. And I tried to understand the rules a little bit and to see if I could adapt them. Here was a first attempt, so starting with something, once again, square, very simple, and selectively subdividing it further and further and further. And then just extruding it, which brought out something like this, or like this. I don't know where that one went, but Sorry, are you? Yeah, now you see something. This is also where I really ran into difficulties. How can one create this kind of a form? How can one produce this kind of a form with a limited budget? I didn't know how, and I tried to simply turn the surfaces into tubes like here, and quite naively to hang them from the ceiling. I think only moderately successful, because one can't really discern the original patterns that were there anymore. It gave a different effect, but not quite the one that I had intended. 2 grottos. This is, I think, a project that I've been working on a long time, together with a friend at ETH who was originally supposed to be here tonight, Benjamin Dillenberger. We received a commission to create a grotto, and I knew very little about grottos. There's a couple in France and Italy, in these Baroque gardens. They're always somewhere between man-made and natural, combining elements of both. And this was a commission to create a grotto that a person could walk into, and that it should be digitally fabricated and computationally designed. The idea being that from this curator who commissioned it at FRAC, that these procedural approaches that one uses, these computational approaches, also often are somewhere between the man-made and the natural, and that this dialogue has been historically exemplified in grottos, and there's thus a parallel. Here is our initial sketch for one of the grotto walls, and how we imagined it. The idea of a room one could walk into with multiple perspectives, with hidden information that you can kind of approach at different scales, that you'll want to explore it. This is how we imagined the surface detail, and we had no idea how to produce it, and then stumbled upon the machine that I showed you at the beginning, this very large printer. It produces sand, and it glues sand. And these were our very first tests of printing a few pieces. We imagined the room. We didn't quite dare to build a roof. We thought, we don't know how it's going to behave. But we imagined 2 sides and a space in between. And while this printer can create massive pieces, 4 by 2 by 1 meters, 8 cubic meters, it turned out that these weigh 13 tons, and nobody can lift them or display them. We broke it down into what are essentially these Lego bricks. And then started a very happy time, because then we realized, okay, maybe we can do this. Let's have fun. Let's play. It wasn't, as was mentioned in the intro, it wasn't so much about efficiency or function, but just about a sensation ultimately. It's a design in 3 dimensions, so it wasn't done using plans and sections or elevations, but arguably more like a sculptural approach. And the interesting thing is, in a way, there's usually in architecture, you have a lot of adaptation to bring your design to fruition. Here, what's in the computer, you can essentially press Control P and the printer prints it. It's a fabrication without adaptation. A fusion of structure and surface. So in the past, you often had coarse bricks and then, I don't know, a nice marble on top of it. Here, it's structure and surface are one material. And again, something between natural and man-made, between chaos and order, between the foreign and the familiar, between the expected and surprise. The museum insisted on floor plans, so we had to write a script to actually create floor plans, but they weren't there initially. And I had hoped to make the whole thing in gold. And here we are with gold plating, and then we realized the calculation was completely off by about 2 zeros, that gold is very expensive. So we stopped that, and then we went over to fake gold, and then we realized that the time to do this is also very expensive, and in the end it was spray painted, which looked so terrible that we went back to white. And here is just a very brief film that shows the printing of the full-scale version of it. So again, it's regular sand, which has been filtered to a certain size, that gets applied in a very thin layer, about 1/8 of a millimeter, and then it gets selectively glued together. And the sand that is left over simply gets vacuumed out, and it can be reused. It's almost like an excavation process that goes on. This is a very small piece. Again, you could do 8 cubic meters at once, and then at that point start a very laborious process of removing the sand. Now that's automatic, but back then that was still very much a handmade process. Finally, things are infused with resin to strengthen them, and are painted. And this process is usually was used in the past to create casting molds, casting parts for engine parts, for ship propellers. But we thought, okay, maybe if we coat it and reinforce it, we can use it as actual architectural elements, as bricks. This is a test setup, so the gaps are very big in this. This was because the floor was not very straight. The actual one was a bit more successful. So again, the idea of a space that you can walk into and explore. And here the assembly of these Lego bricks. I'll fast forward a bit and show you just some of the pictures of the first half that was printed. And if you look here, you can see that it is, again, there's a side wall that's missing. It's the same process once again. It is a cube that was divided, and much like with the column that I showed you, simply cut open. And you're looking at the division that took place in the inside of the form. And this gap between the virtual and the physical, it began to close. So it took 10 days of print time, but only because they were printing so much else in between. I think if they would have done only our project, this grotto would have happened in slightly more than 24 hours, maybe 30, which is relatively quick. This was a successor project where we tried to increase the resolution a little bit. We were quite happy because we felt there's more texture and more detail. And then this happened, and this is not Photoshop. Then this beautiful butterfly landed on the space, attracted by the glue, I guess. And then we realized, okay, we are far away from nature, far away from what we are. We have a long way to go. We tried to scale it up. This was for a competition at PS1, which is a museum in New York, which in their courtyard always has great parties in the summer. A temporary installation. We imagined elephants and giraffes and a big fountain and DJs and dancers, and we block, and he was tapping his feet, and we thought, we got it, we're going to win. And then we lost to a guy who built an aqua purifier, which also actually turned out quite interesting, but we would have liked to build it. But we did have the chance to build a second grotto, and this time we thought, okay, with the first grotto, the idea was really, can we print something at an architectural scale? With the second grotto, it was the idea of what can the printer actually do? And one thing that the printer can actually do is, which is very hard to produce, is to create porosity, to create multiple layers. So not just a single surface, but something porous or perhaps donut-shaped. And here is the process rewritten to create something with, I guess the English term for it is undercut, something that there's something behind. And just a few experiments with this process. So for those of you interested in topology, we were suddenly able to go from the donut or the teapot to the cube or the coffee cup. But I won't bore you with this. But what was more interesting is that we tried to get the computer to not only generate the forms, but to also evaluate them. The way it usually works is the computer produces very many forms, and then I have to sit there and think, okay, this one is good, we're going to take a little bit more of this one, we're going to combine them, we'll let it run again overnight, and so on. I thought, what if the computer could also evaluate its forms and decide on its own which one is good? What if it could learn to produce something that one finds, if not beautiful, then interesting or appealing? I don't know what the term is. And I teamed up with a firm in Munich, a computer firm, and we produced 1,000 forms by this process, and we just essentially bribed the employees to evaluate the forms. They would see two forms on the screen, and they could either choose right or left, or right or left. And if they did enough of these evaluations, they had the chance to win a trip. And we also made sure that they were actually looking at the forms. So if you went like this too quickly, then there was a disqualification. But after a while, we had a good idea of which of these forms, for some reason or other, we don't know why, were more appealing and which ones weren't. And then we tried to get the computer to learn to understand, this was a very early AI project, what it is that is appealing. We never found out what it is because it was a black box, but at the end the computer was very good at identifying forms that people thought were appealing. The forms that came out had a very specific aesthetic, and I suspect it's related to the people that were doing the evaluation. I'm sure if one would have done this in a different country, in a different context, with a different age group, maybe the computer would have optimized completely different forms. But I thought to myself, okay, now we've done this. Now let the computer decide how the second grotto is going to look. I'm not going to intervene anymore. And these are some of the forms that the computer came up with, where the computer thought this was the end of this was at an optimum or near optimum. It thought that this was a form that it could no longer improve. Are they nice? Are they not nice? I don't know. But I thought, okay, it's all been about giving the computer more control, about taking a step back, about adding a level of abstraction. So I decided not to edit them, but to simply accept them. And the one thing that I did was to essentially paste these forms together, and that became the second grotto, which you can see. Sorry, that's a bizarre transition. Sorry, which you can see right here. Is this? Yeah. And again, there's this one has I think is more three-dimensional. It has more different layers than before. So again, the idea of a space you can walk into that you will hopefully find interesting enough to spend some time looking at, or that you'll want to reach out and touch At the museum, they always say, no, you have to put up a do not touch sign, but I think quite the contrary. Let people touch it, and we'll spray paint it afterwards. Here is this second grotto, and a few of these details. This is, I think, of the ones that the computer came up with, probably one of my favorites, spots, locations. This is one I quite liked also. But there are other parts that I think are just far too cluttered. So what is the best way to work? How much control does one give up? How much agency does one assume? I'm still looking for the optimum. And this is a same project along the same vein for BMW, where we just said, okay, let the computer populate a three-dimensional space, and then we'll try to build it as a theater with 4 walls, and then people can be in the space, and let's see what they discover. And once again, this is trained on these. The training is the same on these tech guys who've been watching, I think, a lot of World of Warcraft or something like that, and that's why it looks, I think, the way it looks. And it would have been a dream to rerun this experiment, as I said, in a different context with different people, maybe with children, maybe with people in retirement home, maybe with who knows, and to compare the worlds that in the end come up, and that in the end one can kind of be surrounded by or enveloped by. This thing, actually, people hated. People walked out of the room pretty quickly because they found it too aggressive somehow. When we had this lighting effect was better, but maybe it was also the sound. But it made people uncomfortable, I think. We built one of the forms that the computer produced, made it quite big, 6 meters. And that's what you're looking at here. At a larger scale yet, Romeo Castellucci, an opera director, approached me, and he said he liked this initial grotto and could imagine it as a design for his opera, the Zauberflöte, the magic flute, Sarastro's Temple of Light, so the rationalist guy against the nocturnal mother-female role. He was supposed to be in this. And then I said, okay, this is wonderful, but you know, the opera stage is very big. Do you know what you're getting into? And he's just like, yeah, trust me. And then we began. It was crazy. One couldn't 3D print this because it was too heavy. So this is robotic milling of EPS and then coding. It was fabricated in Spain, actually, at a company in Madrid called Factum Art. It was just a gigantic pleasure to go down there, and suddenly I was walking in the space that I designed. We broke it down into different parts so that these parts could move on the stage, so that this grotto could gradually be assembled, and so on. We also strengthened the parts so that people could climb. You'll see in a second, people could climb onto it and engage with it, and it turned out to be very big. The opera starts, and there's only one part visible, and then slowly the other parts come onto the stage. You can see in the corners are some dancers in the back also, and Sarastro is here. This was the piece as it was fully assembled. Could you turn it up a little bit? Thank you. There you can see the parts moving together. The stalactites would descend from the ceiling, and suddenly this stage came together. So it was a very nice moment for me. I think I finally had the courage to study to become an architect, as was said, when I was watching an opera, and then to sit there and design an opera stage, it was a great joy. I will leave you with one final project. It's called the White Tower. It's a project that Benjamin and I have been working on for the better part of four years now. It's hard to believe. And it started actually at ETH, where they have a very big, that's a university in Switzerland, where they have a very big digital fabrication lab. And they've been doing research in concrete printing, which is not only going on at ETH, but in many parts of the world. This is led by Anna Anton. And the idea with this concrete printing is simply to deposit concrete in layers by a robot. And to have these layers be solid enough, to harden quickly enough that they adhere to each other, but to not be so solid that they all fall, not to be as liquid as to fall apart. Why would anyone look at concrete printing at all? I think one of the reasons is the prospect of material reduction, that you can print components that are hollow. You can fortify components only where it's needed, and by reducing concrete material, you can reduce CO2 ultimately. The other nice thing about it is that you don't need formwork anymore. Often, if you produce a complex shape in concrete, you need to create an elaborate wooden formwork that, in most cases, then is simply thrown away afterwards. And But why don't we see very many multi-story buildings out of this technology? It's because their concrete needs metal inside, needs rebar inside to be strong, and it's always been a challenge to combine these two. I spoke earlier about the potential for ornament that you have in 3D printing, or the potential for mass customization, for having individual components, and that's one thing that you do have in concrete. You don't have as much formal expression and freedom as in 3D printing when you're making a grotto, but you can begin to create a what I call or we call a material-driven ornament. So you can play with the materiality of this concrete, which you can make it a little bit more liquidy, you can make it harden a little bit slower, and it begins to drip, and it creates its own type of ornament, which you can try to bring out. This tower, so there is a village up in the Swiss Alps, and there is a cultural festival by the Origin Foundation, which got in touch with ETH and to see if one could do a project together bridging culture and technology. The village is not that small, but there's only 14 people that still live here. It used to be a very prosperous village, but everybody is moving to the city, people aren't having children, and the village there's only a single child remaining, and the village may die out. And the curator wanted to construct a tower. This tower was supposed to have two roles. It was supposed to serve sort of as a beacon in the village to get people to stop at this village because it's on a pass road and everybody just drives by it. And at the same time, it was supposed to house a theater inside. This is the design for the tower at what was a very long process, also with structural engineers. You can see these columns which are truss-shaped, and that's to make them stronger. And the design concept is essentially it's like a vertical enfilade of rooms. It's in castles. You used to have a sequence of rooms horizontally, and we thought, okay, let us make them vertically different rooms with different atmospheres. So you start at the bottom, and it's very dark. You have thick columns, and as you ascend the spiral staircase, it gets airier and airier and lighter and lighter until you get to the top, where you have a very small performance space. It houses only 40 or 45 people. But you could have musical performances, a string quartet, an opera, not an opera, sorry, somebody singing songs, and so on. In the summer, it's completely open, and in the winter, the idea is to cover it with foil. to permit you to use it, because it gets, of course, very cold. It's at 1,600 meter elevation. Here you can see the village again. And I'll show you a quick video about it, just because the video shows some of the structural details. It's built on top of an existing historical building, which is at the bottom. And there are 32 columns. Each one is unique. And one of the core innovations here is that there's two robots that are working in parallel. A first robot deposits the concrete, and a second one takes rebar rings and places them inside at regular intervals. It's slightly fast forward here, but it takes roughly 4 to 5 hours to print a single column. And you can see these red lines that you're seeing, that is the vertical rebar that is inside these columns. We worked with a structural engineer that is very famous in Switzerland for creating very elegant bridges. An older man, everything was still hand-drawn, which was quite a interesting compliment to the way that we worked. And I'll show you just now. Here are some structural tests that we performed to see if it would actually stand up. And then we began to produce the components. The initial idea was to produce everything locally in the mountain on site with a robot, but it turned out it's so cold up there that one can only print really for about 2 months per year, and the other 10 months one would have to construct a building around it and keep it very warm. So the fabrication actually took place at ETH. Here are the columns now in a local hall being brought to site by a truck. And it was great. I have to say, it was amazing it was 3 years of working on this. It was amazing to see it happen. Finally, these columns floating through the air, a very, very happy time for myself. This is the top floor. There's a cupola that goes on top, which is not in these pictures yet. Yeah, a very large crane essentially takes these components, always 8 per level, which are prefabricated, and puts them in place. And the assembly is actually really quick. A floor takes, to assemble one floor takes about a morning. By noon, people are usually done and having lunch. I am terribly afraid of heights, so taking these pictures was a challenge. This is the inside of the tower. There's a spiral staircase that is now in it. And this tower is very small. We have a diameter of about 8.5 meters at the top, not more, and 6 at the bottom. Has a height of 30 meters. And this is a view through the tower from level to level before the stair was put in, I think. And so on the top, you have an 8-meter high room, approximately. And here again, the picture that I showed earlier of some of the structural ornament, material-driven ornament that these columns can produce. And the algorithm to do this was in a way trivial compared to some of the other ones, but it was nonetheless I thought was very nice is once we had specified a certain form for the columns in terms of undulations, we said, okay, let's open it up. Everybody in the team has to then design their own column. And so if you go up the stair, people can say, okay, this one was mine, this one was mine. There's a big debate about which one is the best one. It's not mine. Here are some very recent pictures. These were taken just 2 days ago. So this is the metal staircase inside. and we're doing some lighting tests and some tests of foils. It's set to open in 2 months. I hope very much you guys will come and visit at some point. Maybe not all at once, because there's room for 40. So where are we now? I think to summarize, I think we're at a point where we need to understand the computer not only as a partner in design, but arguably also as a muse. And we should let the computer inspire us and perhaps, and this is controversial in the days of AI, but perhaps to help us to be creative. The computer to expand our imagination, and I think at least initially we need to lose ourselves in it. I think we can then regain our agency, regain control, but it's going to be a balance between these two, between surprise and control, and I think that's where some of the potential of this technology lies. So I see the computer, I think, as a tool to draw what perhaps before was not drawable, or to imagine what perhaps I wouldn't have imagined otherwise, and to celebrate the unforeseen. I leave you with one of my favorite quotes by Louis Kahn. He was teaching in 1971, I think at Princeton, I'm not sure. And he gave this example to his students. You say to a brick, "What do you want, brick?" And the brick says to you, I like an arch. I want to be an arch. And if you say to the brick, "Arches are expensive. I can use a concrete lintel over the opening. What do you think of that, brick?" And the brick says, "I like an arch." In other words, it's in the nature of the brick to want to become a vault or an arch. So maybe the question that we have now for us today, with all the freedom in digital fabrication and computation, is what would a grain of sand like to become? And I will leave it at that. Thank you very much. Thank you. Oh, sorry, you can please mute this if there's a way to. Could you turn off the sound? Thank you. Could you turn off the sound? I can't mute it. And I'd like to open it up for questions, please, if there are any questions. Yes, I do. I have 2 or 3, but I'm afraid I'm unable to talk about them at this point, because one is in Taiwan and one is in France, and I think give it another year or so.
Hi, thanks for your talk. I was wondering, in the beginning you said there are no constraints, or like almost no constraints. So I guess the material part of it, when you build it, is a constraint. Do you consider that when you're building, or do you just solve that later on?
Great question, and of course I'm exaggerating a bit. It's a bit of hyperbole when I say no constraints. But I like to keep these. I like to give myself the freedom as I'm designing to not think about the way one can materialize it. So initially one leaves the material out. In the case of this tower that I just showed, the material actually influenced the design very much and led to a lot of new iterations as we were figuring out how does it behave, too much of a slope or of an overhang and so on. With the 3D printed projects that I showed, there are really very few geometric and material-driven constraints. I think the moment we got up to an architectural scale, we realized, maybe there are a few that we have to keep in mind to keep it safe. There's always the idea, perhaps one can incorporate these constraints into the computational process, but that's actually quite difficult. I found, at least, because then you're oftentimes in the field of fluid dynamics or something similar, and that's a different computational side altogether, which is hard to bring to unify. with some of these algorithms. Please.
Hi, hello,
Hi.
thank you. I love what you've been talking about with uncertainty, and I was wondering about how your relationship with uncertainty has evolved over time, and how that's impacted not only your creative practice, but other areas of your life as well.
Other areas of my life. Ooh. That's a big question. There's a lot of uncertainty, it seems, in the world right now. But no, uncertainty, I mean, I see uncertainty as in architecture at least, as an opportunity, I think. Because yeah, as I think I was saying, traditionally architects hate surprises. They love to have control of every minute little detail. But I think there are such things as positive surprises. There are moments where I'm really like, wow, I can't believe this came up, or why did this come up, or I didn't anticipate this, and one is able to then incorporate these ideas and play with them. So to me, this is something that I seek out, I think.
Was that in your nature before?
Probably not. No. That's just something that came up along the way.
Thank you.
Thank you.
I wanted to ask something about.
But sorry, just to get back. But I think, thinking about your question right now, and sorry, I'll get to the next one very quickly. I think what has always been important to me is that that I don't want the architecture to be prescriptive, in the sense that I don't want people to tell people, you need to think this, or this needs to cause this sort of an association. And to some extent, I think with these forms, I've had some success with that, because people bring their completely different and own associations to it. Some people will say it's an alien, or an alligator, or a fern, or these different narratives pop up, which I didn't intend, or at least not consciously. And I think this is, in terms of uncertainty, I think this non-prescriptiveness is at least something that I seek out, and which I think probably reflects other parts of my life as well.
I wanted to ask about the materials as well. Is there any material that's probably not possible to make your creations in, that you think would look really cool, like gold maybe, or marble, glass, metal, something like that?
Are there others that I would like to try out, you mean?
That ideally, like if
yes,
you could,
what
do you think would look really, really cool that's maybe impossible to
There are a million.
realize?
There are a million. I wasn't going to show this, but maybe I will. This is, oh, you can't see it anymore, but, okay, sorry. This is a project at a very, very small scale. And here we are actually using, it's 3D printed also, but it is plated in 24 karat gold. It is what they call a glorifier for a whiskey bottle. And it is, so it's gold and quartzite, which we used. And it's a very beautiful quartzite stone. We weren't able to mill the quartzite at a very high resolution, but it's nonetheless, I was attracted by these materials. The dream is always to do something in marble, and there we are already back at the question of what the next project is, and I hope to show it at some point in the future.
Hello.
Hi.
Yeah. Sorry, I know you can't talk about too much about your upcoming project, but you mentioned about your next or like few works will be in Taiwan, and I was wondering, in Taiwan we have a lot of earthquake, so I was also wondering, like, how would you overcome this?
In Taiwan you have a lot of earthquakes. Yes, that's true. I think, and actually, in the tower project you saw up in the Swiss mountains, it's also an earthquake zone, and it's not only that; it's also a zone of strong winds. So the tower is designed to very high structural standards. I'm not sure one would be able that they would be sufficient for Taiwan. I don't know. On the other hand, the building is 30 meters high. I think in the end, if one were to build something there, you work with a local structural engineer. in Taiwan and Japan, there's such innovative ways of countering the earthquake, whether you build on sort of a rubber base or whether you have a swinging pendulum inside, like in the Taipei 101 building. I'm sure one could incorporate something like this.
Thank you.
Thank you.
Hi.
Hi.
Sorry, I wonder what happens with these structures
Wait,
after.
sorry, you're there, okay.
What happens with these structures and the iterations, like after they have fulfilled their purposes? Like, what's the process of?
Good question. I'm glad you asked, because with this tower is supposed to be standing only about 5 years. It has been put together, it's been designed with disassembly in mind. So we have, in putting it together, we haven't used any wet joints, as I say, but only dried joints. Everything is simply screwed into place, and these screws can very easily be undone. And the tower, just as you saw the assembly take place, it can be disassembled. It could be disassembled and the components become part of something smaller or bigger, or you could imagine 2 towers next to each other, or you could imagine it being rebuilt somewhere in a completely different place. But there is this idea of reuse and disassembly, which we paid much attention to and which complicated things, but it's, I think it's going to be interesting to see what happens.
For example, for the project that you showed that were painted, like, does that affect the material and that cannot be reused or recycled in a future way?
Which ones do you mean?
The one you painted, like with airspray?
The sand material. This one is not meant to be recycled all too soon, I hope, because it's part of Centre Pompidou's collection, and they show it every couple of years. So this is not designed with a disassembly or a recycling in mind. And to be frank with you, the glue makes the recycling difficult for the sand projects. The glue is still the sand itself that gets vacuumed out can be reused and so on, but this combination of glue and the material right now, to my knowledge, cannot be recycled.
Thank you.
Hi.
Hi.
Thank you for your presentation.
Pleasure.
You showed a lot of work that was you collaborating with other forms of art, and it seems like that's also deep in your practice. So I was curious if there's a form of art or science that you're looking forward to collaborating or incorporating into your practice.
Good question. I mean, I think that's a lot of the appeal to me. That I think I'm at the bridge between different things and therefore get to meet different people with different ideas. Sometimes I get invited actually to mathematical conferences, which I think is always great, and other times you have more material science or so on. In terms of what I really liked, I really enjoyed the idea of a performance taking place in this space. I really liked the idea of the opera, or I'm looking forward to performances taking part in the tower, so where you have lighting design, where you have music come in, where you have maybe dance come in, and this is this to me is a great appeal.
Thank you.
Hi.
Hi.
Here, up there, no, the other side.
Yes.
So I stayed a bit with the picture of the butterfly, and I was just wondering if you have any intention of, at some point, make a project of more like make it not that, because you said with the butterfly that it was super distant, like the nature for your projects. So I was just wondering if you have thought or have an intention of merging it a bit, or somehow integrate a little bit more of nature in any of your projects.
I think I mean, the nature is definitely there as a source of inspiration for me. I think 10 or 15 years ago, I thought there was perhaps a parallel between this process of division that I showed and maybe the division of cells in the creation of life in biomimesis. But I think at this point, that was a naive thought in retrospect. Nature is so much more sophisticated than anything that one is doing and approximating. So I think, to me, it's rather than trying to recreate nature or something, I'm perhaps more interested in what is in the nature of these processes that one can bring out.
Hi. My question is about the hardware you use to create all of this intricacy. And for example, you're using billions of voxels in the Italo Grotesque in this project. So do you really use like really high hardware, like has a really potential, or is just a normal computer? Or?
It was back when this first Digital Grotesque project happened. This was in 2013, I believe. At that point, we had to use ETH's strong supercomputers just because memory was an issue. But by the time the second and third one came around, a personal computer could do it. I mean, it's a personal computer with a lot of memory inside, but no, it's not a lot of hardware. Processors haven't gotten much faster. You just have this parallelization, and which necessitates having to rewrite everything. But nowadays, any computer can do it.
Thank you.
Hi. In the middle, like just here, up in the middle.
Yes.
Yeah,
hi.
There I am. So I'm wondering a couple of stuff about the second grotto.
Yes.
I think that's the one that you presented in this performance, that kind of opera.
Yes.
So it seemed really massive. And I'm really concerned about the scenario. I don't know if it was hard to build it into the scenario. Do you do a kind of reinforcement for it? And also, do you have any kind of parametric consideration that you put into the computer so it considered like the way to behave like in the way that it's supposed to behave? And the second part is about the surface. When you were talking about it, you show this idea of this surface like it was really polished, really kind of shiny.
Yes.
But with the glued sand, I don't know if you polish it or how do you make it to work, because it has so many forms that it's hard to polish, or maybe you cover it. How did you work with it?
Okay, so with the first grotto, yes, there is a substructure in it. It's made out of this big one that I showed. It's made out of EPS, but there's an aluminum structure inside that just stabilizes it. And also because what you didn't see is that these pieces on the back, they have lights integrated that shine onto the pieces behind them and so on. So there's an actual theater infrastructure integrated into these pieces. This grotto was indeed coated, and that was the wish of the director to have it shiny and glossy and wet looking. With the sand you can also coat, but and we do, but in what I showed there wasn't any. We decided to keep the structure of the sand visible, so we didn't gloss it over. I think if you add a resin coating on top, which we've also done, it gets smooth, but we wanted to actually let people see what the material is made of. And did I answer your question? Yes, okay. Thank you very much, guys. Thank you for all of your questions, and thank you for coming.